Welcome to The Explainer. Today we're diving into the anatomy of a programming solution. And look, we're not going to get bogged down in syntax here. Instead, we're analyzing the pure architectural framework that separates a flawlessly functional solution from, well, an absolute chaotic mess. Let's get right into it.
So, where does a programming task actually begin? I mean, we've all been guilty of diving straight into our IDE the absolute second a deadline looms, right? But the truth is, if your very first step is opening up a code editor, you're already setting yourself up for technical debt. The real architecture, that happens way before you type a single line of code.
To really grasp effective software design, we have to respect what we might call the grand divide. A typical programming task fundamentally splits into two distinct halves, the problem-solving phase and the implementation phase. And the golden rule here is that problem-solving must entirely precede implementation. You literally cannot write an efficient program without mapping out the logic first.
You see, the workflow divides the heavy intellectual lifting. The problem-solving phase is what produces an ordered sequence of steps. Only after that logic is totally locked in do we move to implementation. Actually translating that solution into Python, Java, C++, whatever you're using. The actual solution is created conceptually first, not in the code itself.
And the output of that first critical phase? It's an algorithm. Now, simply put, an algorithm is just an ordered sequence of steps that describe the solution to a problem. Just like a data pipeline requires precise, sequential operations, like extracting data, transforming formats, loading it to a database, solving any digital problem requires a perfectly ordered set of logical instructions. This algorithm is basically the ultimate triumphant output of your problem-solving phase.
Okay, so let's do a deep dive into analyzing the problem. How do we actually arrive at that ordered algorithm? Well, we don't just guess, obviously. We perform a rigorous analysis of the problem at hand to lay out specific requirements. Every good developer uses a four-step checklist. First up, inputs. What raw data is actually going into this system? Second, expected outputs. What exactly is this program supposed to produce? Third, special constraints or conditions. Are there limits on time, memory, or, specific business logic rules the data absolutely has to follow? And fourth, formulas or equations. What's the mathematical or logical engine doing the heavy lifting? Imagine you're building a simple navigation app. The input is your current location and destination. The output is the fastest route. The constraint might be avoiding toll roads. And the formula? That's the math calculating the distance. You've got to have all four.
Analyzing the problem strictly requires identifying all these specific components we just talked about. If you skip even one, like, say, failing to account for a constraint where a user enters a negative integer, your final program is going to silently fail, or it's going to produce a massive bug down the line. Nailing down your inputs, outputs, constraints, and formulas is completely non-negotiable if you want to design a reliable solution.
Moving on to the next phase, bringing it to life and representing the algorithm. So, we've analyzed the problem, right? We know the logical steps. But now we need a way to communicate this ordered sequence clearly, both to ourselves and to our team, before any actual coding begins. Typically, we use two distinct methods to represent this logic: pseudocode and flowcharts. Pseudocode uses structured language without the strict, nitpicky syntax of a real programming language, making it perfect for developers to just quickly outline logic. A flowchart, on the other hand, is entirely visual. It maps the exact journey of the data. And honestly, that is incredibly useful for getting on the same page with non-technical stakeholders or mapping out complex state changes.
Basically, an algorithm can be represented using pseudocode or a flowchart as your definitive bridge. Think of it like the final blueprint handed over by a master architect. Once you have this tight, well-thought-out documentation in hand, the problem is officially solved. You are finally ready to cross that grand divide we talked about and jump right into the implementation phase.
Which brings us to a final, pretty crucial thought for this explainer. If coding is really just the mechanical implementation of a solution you've already designed, what real-world problem are you actually solving first? The next time you're facing a massive task, whether you're refactoring a legacy system, automating a data pipeline, or building out a brand new microservice, resist that urge to just start writing syntax. Step back, take a breath, analyze your inputs and outputs, draft your algorithm. Always remember that the true superpower of a developer lies squarely in the problem-solving phase. Thanks for joining me on The Explainer today, and I honestly can't wait to see how you apply this framework to your own projects.